Hello, students. Let's begin with an interesting thought. Imagine walking into a perfume shop, dozens of bottles, all different scents, yet each fragrance comes from molecules carrying certain special groups that decide how they interact with our noses. In chemistry, those special parts of molecules are called functional groups. Now, in this chapter, we are dealing with oxygen containing functional groups, alcohols, phenols, and ethers. Each of them has oxygen, but the way that oxygen is bonded and hybridized completely changes how the compound behaves. Functional groups are like the reactive handles of molecules. They decide acidity, solubility, boiling points, and most importantly, the types of reactions the compound will undergo. So, if we can picture the structure, we can predict the chemistry that follows.
Let's start with alcohols. The oxygen atom in the hydroxyl group is sp superscript 3 hybridized. That means it has 4 regions of electron density, 2 are bonds, one with carbon and one with hydrogen, and the other 2 are lone pairs. Because of lone pair repulsion, the COH bond angle is about 104.5 degrees, slightly less than the perfect tetrahedral angle. This bent structure makes the CO bond polar and the OH bond polar too, allowing alcohols to form hydrogen bonds. That's why ethanol has a higher boiling point than compounds of similar molar mass like propane. Picture ethanol on the screen, a 2-carbon chain with an O group attached, oxygen carrying to lone pairs, and the bent geometry. No resonance occurs here, so the acidity and reactivity depend mostly on whether the hydroxyl carbon is primary, secondary, or tertiary. Now let's look at phenols. Here, the hydroxyl group is attached directly to a benzene ring carbon, which is sp superscript 2 hybridized. That changes everything. The OH bond is still polar, but the lone pair on oxygen can interact with the pi electrons of the ring. When phenol loses a proton, it forms the phenoxide ion. Thanks to resonance, the negative charge is delocalized over the ortho and para positions of the ring. If you follow the resonance structures on screen, you'll notice how the negative charge shifts around the ring, making the conjugate base much more stable. This is why phenols are stronger acids than alcohols. Also, the bond angle at oxygen tends to be slightly larger than in alcohols because resonance alters the electron distribution. This structural feature explains why phenol behaves differently in reactions like electrophilic substitution compared to ethanol. Now let's move on to ethers. Their general formula is ROR prime. Just like in alcohols, the oxygen is sp3 hybridized. It forms 2 sigma bonds with carbons and has 2 lone pairs. Because of this, the geometry around oxygen is bent, and the COC bond angle is about 110 degrees. But here's the catch. There is no hydrogen bonded to oxygen. That means ethers cannot form intermolecular hydrogen bonds like alcohols do. The result? Ethers are more volatile and have lower boiling points compared to isomeric alcohols. For example, diethyl ether, once used as an anesthetic, is highly volatile and evaporates quickly. On screen, look at the structure of diethyl ether. Oxygen with lone pairs, 2 ethyl groups on either side, and the bent geometry. This small structural detail explains a huge difference in physical behavior. Let's now compare alcohols, phenols, and ethers side by side. Alcohol oxygen is sp superscript 3 hybridized, bent, and can hydrogen bond strongly. Phenol oxygen is also sp superscript 3, but because of resonance with the aromatic ring, phenols show higher acidity. Ethers have the same hybridization, sp superscript 3, but lack hydrogen bonding due to the absence of an OH bond, making them more volatile. These structural variations explain trends in boiling points, solubility, and reactivity. For instance, Alcohols dissolve in water better than ethers because of hydrogen bonding. Phenols are slightly soluble due to resonance but still acidic enough to react with sodium hydroxide. Ethers, on the other hand, are used as solvents precisely because they are less reactive. So you see, small changes in geometry and bonding lead to very different chemical personalities. Let's solve a common reasoning problem. Why is phenol more acidic than ethanol? In ethanol, when the ethanol bond breaks, it forms the ethoxide ion. The negative charge sits entirely on oxygen with no delocalization. That makes it unstable, written as CHCHO plus H. But in phenol, losing a proton gives the phenoxide ion. Thanks to resonance, the negative charge spreads across the benzene ring, especially at ortho and para carbons. If you draw the resonance structures, you'll see multiple equivalent forms stabilizing the ion. That's why phenol gives up its proton more readily, written as CHO plus H. So the key difference lies in structural stabilization of the conjugate base. Resonance makes phenol acidic, while ethanol stays neutral in comparison. This type of reasoning is often asked in exams, so make sure you can explain it step by step. Finally, let's wrap this up with applications. Alcohols, because of their hydrogen bonding, are used as solvents, fuels, and disinfectants. Phenols, thanks to their acidic nature and aromatic resonance, are found in antiseptics and polymers like bakelite. Ethers, being volatile and less reactive, make excellent solvents and were historically used as anesthetics. In industry, chemists rely on the structural understanding of these functional groups to design drugs, polymers, and solvents. In exams, expect questions on acidity order, boiling point trends, and resonance, all of which come directly from the structures we just studied. So to sum up, alcohols, phenols, and ethers may all contain oxygen, but the way that oxygen is bonded and hybridized changes their entire behavior. Mastering their structures is like unlocking the blueprint for their chemistry. I hope this session helped you see how much structural details matter. Chemistry is not just about memorizing formulas, but about connecting geometry, bonding, and real-world use. Until next class, keep exploring the molecules around you, from sanitizers to plastics to solvents, and see how their structures shape their functions.